Belum kelihatan deh. Harus
sekali aja.
masih sholat asar dulu di malam.
Udah tadi.
Duluan.
Udah tadi.
Baik, Bapak Ibu sekalian, selamat sore. Salam sejahtera bagi kita semua. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Untuk berkat waktu, mungkin saya akan buka sekarang, Bapak Ibu sekalian. Mohon izin, mungkin saya tidak bisa menjawab satu persatu. Mohon izin Bapak Ibu sekalian. Mungkin hari ini, alhamdulillah kita berkumpul di tempat yang baik juga dan waktu yang baik juga, alhamdulillah, dalam acara webinar series keempat ya Pak, ya. Dengan topik perencanaan dan pembangunan bendungan beton. Acara ini terselenggara oleh PT Beratas Abibaya, Bapak Ibu sekalian. Kemudian pada hari ini direncanakan akan ada dua paparan dari beberapa dua narasumber. Yang pertama adalah dari Profesor Feng Jin, beliau adalah dari Changjiang Scholar Chairman Tsinghua University. Kebetulan beliau sudah hadir. Thanks for coming, Mr. Feng Jin. Kemudian yang kedua adalah Dr. Didi Jarwadi. Beliau adalah Ketua Komisi Teknis Seismic Aspect of Dam Design KNBB. Beliau akan memaparkan terkait dengan seismic design of concrete dams. Kemudian acara ini juga akan dimoderatori oleh Dr. Insinyur Aris Firman MSc. Terima kasih Pak atas kehadirannya. Kemudian pembahas oleh Pak Profesor Dr. Eko Winar Irianto MT. Mungkin mohon izin Pak Eko sudah hadir. Baik, mungkin akan menyusul. Kemudian acara ini mungkin akan ada diselingi oleh door prize Bapak Ibu sekalian. Ada 3 door prize kurang lebih yang akan kita bagikan hari ini. Mungkin door prize pertama setelah Bapak narasumber memaparkan paparannya, kemudian setelah itu dilanjutkan dengan tanya jawab, kemudian dilanjutkan dengan simpulan. Nah, setelah itu baru akan ada door prize 2 door prize lagi yang akan dibagikan. Mungkin untuk menghemat waktu, saya silakan kepada Pak Aris Firman untuk mengawal acara ini, Pak. Terima kasih, Pak.
Terima kasih, Pak Triaranto. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Selamat sore, salam sejahtera buat Bapak Ibu sekalian yang terhormat. Mohon maaf, ada hampir 500 peserta yang hadir, jadi saya belum bisa menyapa satu persatu. Tapi pada garis besarnya Kami bergembira sekali Bapak Ibu sekalian bisa ikut kembali di webinar keempat ini. Dan hari ini kita ada dua tamu utama yang akan berbicara. Seperti sudah disebutkan oleh Pak Trihartanto tadi, sebentar lagi mungkin saya akan menyapa tamu kita dari Beijing dulu. Dan sesudah itu nanti Pak Dr. Didik Jarwadi. Izinkan saya, seperti saya janji kepada beliau yang di Beijing, bahwa jam 15.20 mungkin kita mulai dulu dalam bahasa Inggris, karena beliau belum sempat belajar bahasa Indonesia, dan kita belum sempat belajar bahasa Cina, jadi kita pakai bahasa Inggris untuk mempermudah komunikasi yang sejalan dengan materi yang sudah disiapkan oleh Profesor Feng Jin. Good afternoon, Professor Feng Jin. Are you there already? Please unmute your microphone so I can hear your voice. Hello, Professor Feng Jin. Please unmute your phone. Okay.
Hello?
Yes.
Yeah. Yes. Great.
Yes.
Thank you.
Well, first of all, I have to thank you so much for joining our discussion today after our last meeting in ICO conference last year in
Yes.
Ottawa. So at that discussion, we exchanged our views about concrete dams, and we are very grateful to have you now, not only with myself, but hundreds of Indonesian engineers would like
Yes.
to hear also directly from you about this concrete dams. To introduce yourself, we have received your curriculum vitae, and the IT person here will show the CV, but the CV is maybe 17 pages. So I have to take the highlights that Professor Feng Jin is having 17 awards from different institutions. You also have 32 patents on dams, and you include already in dam panel for 7 projects, design review member of 5 projects, supervisor for rockfill concrete dams for 5 projects. You publish 4 books, and you establish also papers about dams, 343 papers. So it is a very amazing, outstanding achievement from you. Congratulations.
Thank you.
So, we would like also later on to have the discussion after your presentation of about 45 minutes. The discussion will take about 30 minutes. And I'm very happy also here to have one of our young engineer, Mrs. Anissa Mayangsari, who will be collecting all the questions from the floor. And I would like to invite all the participants also to raise questions through the chat box, and then Bu Anissa will translate that into English and directly address the questions to Professor Feng Jin. Hopefully, the total about 75 minutes will be fruitful for us to exchange views on how to design and how to construct concrete dams. So, the floor is yours now, Professor Feng Jin. Do you want us to show the slides, or do you want to do your slides presentation and the video from your sides? It's up to you.
Okay. Could you see the slide?
Yes, it's now appearing already on our slides.
Okay.
I will check with my colleagues first in Bahasa whether they receive all the slides in front of their gadget. Bapak Ibu sekalian sudah terima semua filenya di depan? Mudah-mudahan sudah ya. Okay, let's start.
Okay, thank you, Aris. Dear colleagues from Indonesia, I'm very glad to be here to via the virtual meeting to introduce some research and application of the one of the kind of the concrete dams invented by myself and my colleagues. It's called rock-fill concrete dams. It's a new type of the concrete dams. And today I will show you some, in my presentation, there are several parts like that. At first, we'll introduce what is the rock-fill concrete, and then introduce some basic research on that concrete, and some of the details of the design and the construction of the RFC dams, and then we introduce some concrete dams in China, the new type of the concrete dams in China. And then at the last part, we will give a very brief introduction to our new kind of the concrete we call self-protected underwater concrete. And then we'll have conclusions. As you know, when we build a reservoir, we usually have mainly two types of the dams. One is embankment dam, and another is a concrete dam. Of course, the concrete dam may be a masonry dam or other we call rigid dams. And usually for embankment dam, it's usually cheap because the construction material for embankment dam is usually cheap. And another advantage of embankment dam is it can be constructed on any kind of the foundation, not only in rock foundation, but also the sand and gravel or other very poor foundation. So the embankment dam can be used in every dam site, but it have mainly a very important disadvantage for embankment dam is when there are a flood overtopping, the embankment dam will collapse. So in the new era of the climate change, there are more and more very severe flood. So the risk of the collapse for the embankment dam is more and more risky. So the important features of the concrete dam is much safer when flood overtopping. And the concrete dam, of course, is usually expensive. And another limitation for concrete dam is mainly constructing on a solid rock foundation. So only the solid rock foundation, we can build concrete dams. And for a concrete dam, we usually say the risk for the failure of the concrete dam is mainly it's vulnerable to thermal cracking. So we have to control temperature control. And the main type of the concrete dam we can usually call the gravity dam, such like that. If we build a concrete dam, then we have to risk the pressure by the water in reservoir, and by the gravity dam we usually have enough safe weight, and then due to the safe weight we can get resistance from the foundation to resistant the water pressure acting on the gravity dam. So we called gravity dam. And another important concrete dam is the arch dam. It is usually it's arch. It's a shell structure. When there are water pressure acting on the dam can change to the action of the horizontal water pressure into the abutment by the arch, the horizontal arch. So we called it's an arch dam. And another important concrete dam is for the buttress dam. Buttress dam, there are many types of the buttress dam, but usually the buttress dam is like just the same like the bridge. But of course, for a bridge, we have many pillars, and then the weight of the transportation will transport to the load into the foundation via the piers. But for the battery stem, the horizontal water pressure is risked by the arch or other structure to the batteries, and we can get a battery stem. And for construction method, we usually have a immersed vibration concrete. We also called conventional concrete. In this kind of the construction period, you can see this picture. You can see we use some immersed vibrator to vibrating concrete to make the concrete compacting. And this, we can see some pipes. This is a post-cooling pipes. The pipes, we can use some cooling water to take off the hydro heat by the cement in concrete, and then we can reduce the risk of the thermal cracking. So we called conventional concrete. Another important method is a roller compact concrete. Just like in these pictures, shows that we use a very heavy roller compact, the vibration roller to compact the concrete, to make the concrete compacting. And another new, we call self-compacting concrete. You can see this kind of the concrete can very easily to flow and to make without any vibrating or roller compacting. The self-compacting concrete can be self-compacting and without any vibration or roller compacting. And in this case, at first we discuss the thermal cracking. Why the concrete we have to face the thermal cracking? As we can see that in the concrete, there are many cement. The cement hydration react will generate many hydration heat. This hydration reaction to give the concrete strength, and also it will induce some thermal stress. And usually for the concrete, especially for the massive concrete, in the concrete dam, the cracking resistance and the hydration heat will make a balance. If the thermal stressing by the hydration heat is lower than the cracking resistance, then the temperature cracking will be prevented. But unfortunately, the concrete, the hydration heat in massive concrete is also always induce many higher thermal stress. So we have to use a temperature control method by the cooling pipe. Such like this, you have to use to embed it some cooling pipe in the concrete and to let the cooling water through the cooling pipe to let the hydration heat dissipate from the massive concrete itself. And this cooling pipe, we have used many temperature control, and it's very complex. So usually we want to reduce the risk of the thermal cracking by the lower the cement consumption. So we have to develop a new method to lessen the cement consumption, and at the same time, we not allow to allow the cracking resistance of the cement reduce. So we have to develop a new method without cooling pipe or other temperature control measurements to let the resistance of the cracking of the concrete is greater than the thermal strengthening. And then we developed a new method that we called rock-filled concrete. It's use the self-compacting concrete and the rock Now we can show some a very simple. We can show a video. This is a process of how to build a dam by a rock filled concrete. At first, we transportate some large rocks. The grain size of these rocks is usually greater than 300 millimeters. 300 millimeters, and we can let the lift of the height of the lift usually from the 1 meter to 3 meters. So, and then we can mixing some very higher performance sapling concrete. This sapling concrete, compacting concrete, can just placing on the top of these rocks, and then the sapling compacting concrete will fill into the voids between the large rocks, and then we can get a solid concrete. And you can see in the lift surface, we let some of the rock is above the surface of the sapling compacting concrete, and then the two lifts between the upper and the lower lift can be bonded each other with these exposed rocks. And of course, these new techniques can let because of they use much of the rocks, so very few cement are in use in these new technologies. And due to of the very few cement consumption, then the thermal stress in this concrete is very lower, and then without any temperature control measurements. And we can see this. You can see in this is a volumetric ratio materials in the rock filled concrete. About in volume, about 55% is the large rocks, the greens with the grain size larger than 300. The maximum grain size of the rocks we usually in the dam may be 800 millimeter or even 1 meter, even 2 meters, if you can transport it. And we have another 45% of the in volume is filled by the self-compacting concrete. But in the self-compacting concrete, we have 24% of the aggregate. The aggregate in self-compacting concrete is usually in maximum grain size of the 20 millimeters. And of course, we have about 9% of the water, and we have usually have the mineral admixture such as fly ash or the sand powder, such like that, with 6%, and only 3% of the cement. So in the rock-filled concrete, we use very fewer cement, and we can get much less cement consumption. This introduce the rock-filled concrete will be cheap and without cooling pipe, so it's very easy to construct. And of course, due to the self-compacting concrete, we need no vibration or roller compaction, and then we can use much less machinery and labor because without vibration, roller compaction, and the cooling pipe. And due to all the compacting of this, the compaction of the RFC, the rock filled concrete, is dependent upon the material or the performance of the self-compacting concrete. So it's very easier to quality control. And then the rock filled concrete will get a much better quality and without thermal cracking. And due to we use very few cement, so it's environmental friendly because we use much more natural rocks. And another advantage is due to this concrete is similar, the performance or the behavior of the RFC is very similar to the conventional concrete or the rock or the RCC. So we can use a very similar design with the conventional concrete dam. We can use the same dam section and we can use less spacing of the transverse joints due to we use the RFC dam has the very smaller thermal stress. And of course, we have to conduct many researches on the RFC. At first, we make some collaboration research with the Northwest University in United States, USA, and we to study the inferior limit of the filling performance of the self-compacting concrete. This we can see some the inferior behavior of the concrete if the performance is below than the inferior limit of the self-compacting concrete. And we developed some method to study the filling performance of the behavior of the self-compacting concrete to the filling the performance of the filling the voids of the rocks. And we developed some numerical methods to simulate the experiments results conducted by us. We also developed some state of the art process, the simulation model we called Lattice-Boltzmann method and hybriding with the distinct element method. And we use the distinct element method to simulate the aggregates in compacting concrete, and we use the LBM Lattice-Boltzmann method to simulate the mortar of the self-compacting. And we can see in this simulation results, you can see that the small circular particle denotes the aggregates in self-compacting concrete, and the large black one is simulate large rocks. And we can see the self-compacting concrete can fill the voids between the large rocks. And if we define a blocking factor, that if the gaps between the large rocks is 2 times of the grain size of the aggregates in self-compacting concrete, is when the ratio is 2, the risk of the blocking will be much higher. So we match less the next bit of the rock voids must at least 2 times of the aggregate size. And due to this, we define a very conservative limitation that the grain size of the large rocks will be larger than 300 millimeters. It is 15 times of the aggregates grain size in HSCC, the high performance self-compacting concrete. In aggregates in HSCC is only 20 millimeters. So the 15 millimeters, the 15 times will be ensure the filling performance of the self-compacting concrete. And we can also to know that the 300 millimeters, the criteria is very conservative. So in the future, maybe the grain size of the rock can be relaxed for example, 250 50 millimeters or even 200 millimeters, such like that. And we also make some many material properties of the rock-fill concrete, such as the strength. We conduct the compressive, the tensile, and the shear strength of the concrete. And we also have to experiment the elastic modulus, the point ratio, and the seepage resistance of the rock-fill concrete, and the free fall resistance of the self-compacting concrete. And we also to test the hydration thermal rise of RFC. And we also study the micro and the priority of the interface between the large rocks and self-compacting concrete. We use BSM to study the micro priorities of this we call ITZ. We can get the conclusion that the self-compacting type have a better performance than the conventional vibration type. So this study to encourage us to build the rock-fill concrete dam in a very high high dams. This type of the concrete we can get a very compacting performance. And also we test the shrinkage and the creep. We can say due to the large proportion of the rocks, the rock-fill concrete, we have a smaller shrinkage and the creep. So this we can get, and we also to study the fracture toughness of the concrete. We can also conclude that the fracture resistance of the rock-fill concrete is much higher than the conventional concrete due to the large rocks. The large rocks can prevent the cracking propagation. So maybe it's similar initial of the cracking in the concrete, but the micro cracking in the rock-fill concrete cannot propagate easily due to the limitation of the large rocks. And then we can get a solution that the density, the strength, the resistance of the seepage and the free flow and the thermal physical properties are very similar to that of the conventional concrete. So this is a kind of the compacting concrete. And the roller compacting concrete has lower cement consumption, and thus we have a lower hydration thermal rise and the shrinkage and the creep. And then the rock-fill concrete has a higher fracture toughness and the fracture energy. So the rock-fill concrete is an excellent construction materials for dams. And then we can introduce some design and construction details of the RFC dams to introduce to Indonesia colleagues. This is we can use the roller compacting concrete to build gravity dam and arch dam. Of course, in principle, we can also build a buttress dam, but till now in China, we only to use the rock-fill concrete to build gravity dam and arch dam. This is a zoning of the gravity dam or arch dam by the rock-fill concrete. Sorry. We can see usually at the upstream, we were set in previous zone. Usually the thickness is half meter to the 300 millimeter to the 600 millimeters, or usually half meters of thickness of impervious zone. This impervious zone is built by only by self-compacting concrete. It means it without any rocks in this zone. And also in the cushion, in the bottom of the body of the dam body, we set conventional concrete cushion. And we can also use some gallery in the dam body. Of course, for arch dam, we can also use impervious zone, and we can set some galleries. And this is a long overflow section of the gravity dam, and this is a spillway. In the spillway, at the spillway, we can use conventional concrete, because the conventional concrete is easy to build in these small regions, and most important, the concrete for the spillway, we have to use erosion resistance, and for that kind of the erosion resistance concrete, the better choice is use conventional concrete. And this is some joints. For example, for the gravity dam or for the arch dam, we will set some transverse joints between the monolith of the different monolith of the gravity dam. This is transverse joints. In these joints, we can set some water stop. This is a 2 copper water stop in this transverse joints, and you can see this in this area. This area is impervious zone. In this impervious zone, we use high performance self-compacting concrete. Here, no rocks, but only this is empty voids. And in the dam body, we use the rocks, but all the self-compacting concrete can be casted, can be placed simultaneously. And if you build RFC arch dam, you can use some keys, and you can also to set up a grounding system at the transverse joints for arch dams. And this is details of the impervious zone. You can say there are some rocks, and this is the impervious zone. Of course, for the impervious zone, there is only high performance self-compacting concrete. So we set reinforcement to reduce the risk of the thermal cracking in this thin layer. And we can use the galleries. You can see around the galleries, you have to set some reinforcement. And if you have a reinforcement, then you can set a void. You can cast it simultaneously, or integral casting by the self-compacting concrete. It's very easy. It's just similar to the impervious zone, that you can say you can get some reinforcement, and in this area there are no rocks, and then the rocks, the voids, and the reinforcement can be casted by high performance self-compacting concrete at the same time. This is details of the construction process. At first, from the quarry, you have a selection, that mainly selection of green sites, usually just by the excavator. The excavator can make the rock selection. If there are many small rocks, then you have to use some real screening to help to rock selection, but it's very few cases. And then if the rock is dirty, is covered by the mud or by the clay, then you can use some rinse. You can some water washing to wash the rocks, because the rocks, the large rocks, have to clean. And then you can translate into the lift and you can use the excavator to help the rock leveling, and the leveling is to maintain the rock is a similar the thickness or the height of the lift is about 1.5 meter to 3 meters. And of course, we can install some formwork. And then after the rock complete, we can use some mixing plant to build the high performance self-compacting concrete and to casting into the lift. And then after the lift, the HSCC casting completed, we had used the green cutting to roughness the surface of the lift surface. And then we need to curing for the raw fill concrete. And then you can get another lift, and then we can get to build the whole dams. This is usually typical layout of the construction. You can see this in this area is a dam body. This is the left. This is upstream. This is downstream, and this is the left abutment. This is the right abutment, and this is a mixing plant. All the high performance self-compacting concrete is mixed in the mixing plant, and just all the concrete is just by a concrete pump through via the pump line into the lift. So without the only concrete trump, it's just by a pump from the mixing plant into the dam lift. So it's very easy to build a concrete dam. And of course, we have some criteria for the large rocks. Usually, the large rocks will have the hard and fresh. What is the hard? We usually, for concrete dam, the height which was higher is lower than 100 meters high. Then the saturated compressive strength of the rocks need larger than 30 to 40 megapascal. The 30 and the 40 megapascal is very easy to meet for usually rocks, and the grain size will be over 300 millimeters, and the surface mud content must be lower than 0.2 to 0.5 millimeters percent. So this is a requirements or criteria for the large rocks. And this is the requirements for the self-compacting concrete. We can say this is a slump flow test, and this is the funnel flow. We set up the index requirements for the slump flow and the funnel flow, and we also define a stability of the self-compacting concrete. That means in 1 hour, the self-compacting performance of the concrete must to meet requirements like that. It's not only in newly fresh concrete, and you have to test in 1 hour. And of course, we can also define the cement consumption in unit of the self-compacting concrete. For example, for 90 days age, the 15 megapascal compressed strength, the minimum cement dosage is only 132. That means because in the roller compacting concrete, the self-compacting concrete is only 45%. So in the roller compacted concrete, the dosage or the consumption of the cement is only about 60 kilogram per kilometers. So all these numbers will be multiplied by 0.45, because only 45% of the concrete of the void of the volume is filled by the self-compacting concrete. And this is some examples of this is a mixing plant, and this is a pipeline to the dam bodies. If there are no suitable site to set up a concrete mixing plant, for example, if you're very far away, then you can use a concrete truck to transport the concrete into the dam site. And this is how to place the concrete, the self-compacting concrete into the rock fill by this method. We can use such like S or return method from the upstream to downstream. And of course, we can also use many kinds of methods to build, not only by the concrete pump. For example, if you can just by the concrete tramp, or by some chute, or by some excavator, or just you can use the cage. Any kinds of measurements, if you can use, depends upon your prescribed conditions. And after the HSCC placed completed, then you can use a crane cart. You can see in the surface there are many rocks exposed in the lift surface, and you can use the crane cart. And we can show some RC dams in China. In China, until the end of the 2019, the last year, we have completed 79 dams. And now we have 41 dams is under construction. And the highest roller compacting concrete dam for a gravity dam is reached 90 meters. And for arch dam is 69 meters. And this is the location of the built or the under construction dams in the China. So you can see from the north part to the south part. And this is the highest RC dams in Yunnan province. We call Songling rock-filled concrete dam. This is the upstream, downstream, and this is the built, and this is the dam. And with some other RC dams, for example, this is the Xiaojiang Arch Dam, and this is a Maopo dams. This dam you can see many. This is a gallery, and in this Maopo Arch Dam, the height of the dam is 43 meters, and all the concrete is built in seven months. 7 months, so it's built fast. And we can see some Koushan gravity dam, Weitan gravity dam. This dam is completed in 1910. So this dam is operation more than 10 years. So the endurance of this concrete is verified. And this is the highest arch dam. This is the highest arch dam, Baija double curvature arch dams. You can see this is how to build it. This is a concrete and the quarry and the rains by the river, and then the casting of the hypothesis of the self-compound concrete, and this is imperial zone of this dam, and the rocks is by the cage due to this crane tower, a tower crane, and the two tower crane to lift these large rocks into the lift, and this is the Baijia dams under construction. And we also built a Lutang RC arch dam. This dam we can see without transverse joints, so the whole dam is integral casting. We can see some and in this dam we use some precasted concrete to build as a formwork, and then the rocks was transported by the cage, and this is the rocks. This is a formwork by the precasted concrete blocks, and this is the loading of the rocks and the lifting of the rocks. This is some embedded parts for the monitoring items, monitoring the lift pressure, monitoring the thermal temperature rise, such like that. And this is to monitor the formwork by the precasted rocks, and this is to check to monitoring the construction quality of the rockfill concrete. And this is a Mongshan arch dam completed. And till now we issued some standards. For example, this is for in 2014 by the Water Resources Department of the People's Republic of China, and this is by the National Administration for Energy, and also we have some English version. So if you want to get to read some Chinese standards for the rockfill concrete, you can buy it. We have some English version of these standards and the codes. You can, if you want to buy it, then you can email me, and we can help you to buy such like Chinese standards to help you to understand what is the criteria for roller compacting concrete in China. Of course, we also issued two international documents. This is a introductory notes on rockfill concrete technology for dams, joined by the World Bank and the Tsinghua University. And this is we just will be issued in this or next year is the ICOD bulletin on rockfill concrete dams. This we are almost finished and will send to the ICOD before the end of this year. And we have a few minutes. We introduce some new technology for underwater concrete. I think it may be useful for the colleagues in Indonesia. We can show some demo test. This is ordinary mortar or concrete into the water. You can see many cement will enter into the water and make the water very dirty. And if you use the traditional or the dispersed underwater concrete, you use some agent into the concrete, then you can see the water is much clearer. This is the state of the practice of the underwater concrete now. And this is the new method invented by my colleagues and myself. This we called self-protected underwater concrete. You can see the water is keep clear during the concreting, and this is some demo test. You can see this is water, and we can just pass it the water into the water. And in this technology, the water is not the water. It's some solution by our underwater protection agent. So we call UPA. We add some the UPA into the water. The concentration of the UPA is very low, usually 100 ppm. Then we can power the concrete into the water, just almost the same as in land. So you can use the self-compacting concrete underwater, similar in the land. And this is the project. This is a Long Bay 1 rehabilitation project. This is a spillway, but it's erosioned by the flood discharging. This area will be erosioned. And then due to it's in underwater, so we use this method. This is a self-compacting concrete. So due to the self-compacting, it can be just placed into the water without any vibration or other measurements. And then you can see the concrete will cast it into the water. This is the formwork. Of course, the formwork underwater is by the pilot, by the driver, by the diver. And when the concrete was placed underwater, you can see, you can get the ordinary concrete, such like that. And before this, we use some the UPA underwater protect agent into the formwork. Then it's very easy to place the water underwater. So we have a conclusion that the rock-fill concrete technology can be not only used in gravity dam, but also in arch dam. And the broad application prospects of the rock-fill concrete are shown in practical engineering projects due to many advantages. For example, the advantage include the high quality. We have a very good quality of the concrete, and it's economic. It's cheaper than the conventional concrete and roller compacted concrete. In China, usually roller compacting concrete will be cheaper 10% to 10% to 20% of the cost of the roller compacting concrete, and 10% to 30% of the conventional concrete dams. And by employing the rock-fill concrete, we will save the labor and the machinery, and we can use fast construction. Till now, the most fastest construction in China, we built a concrete dam whose height is 58 meters high in 4 months. All the concrete will be built in 4 months. We can build a dam, a gravity dam, whose height is 58 meters. And also at last, we can say the SPARC, the self-protected underwater concrete, is another innovative underwater concrete technology. I think it will be used in the marine and the water resources project and other field. I think that's our introduction to the Indonesia colleagues. Thank you for your attention. And this is my email. If you have any questions after our discussion today, you can email me, and do not hesitate to contact me via the email jinfeng@tsinghua.edu.cn. Thank you. Thank you, Alice.
So this is a very impressive and comprehensive presentation about rock-fill concrete dams. And I would like to give you a few minutes for you to take a break, maybe take some glass of water.
Okay, thank you.
In the meantime, I will ask my chairman of INACO to say a few words to our colleagues here. Saya persilakan Pak Hadi Suprayogi, monggo Pak. Ada waktu buat Bapak untuk menyampaikan sepatah dua patah kata. Pak Yogi, monggo Pak. Kalau sudah bisa di...
No, Pak. I saw in the chat room there are many questions. It's better you respond those questions, Pak. I think. I just see from here, Pak.
Oke, terima kasih
Sorry
Pak Yogi.
for being late.
Moga-moga nanti banyak pertanyaan yang sudah diseleksi oleh Bu Anissa bisa disampaikan ke Profesor Feng Jin dan bisa dielaborasi lebih lanjut. Sekedar catatan saja sambil beliaunya sedang istirahat minum dulu, mungkin perlu saya sampaikan bahwa materi ini setelah saya share juga di bulan November pada saat ada Sarasehan KKB di Solo waktu itu. Karena materi yang sama saya terima dari Profesor Feng Jin waktu ICOLD meeting beberapa bulan sebelumnya dari pertemuan di Solo itu, yaitu bulan Juni 2019. Dan kelihatannya beliau sangat berminat sekali untuk sharing mengenai teknologi baru ini. Dan saya melihat bahwa banyak manfaatnya, baik dari segi terobosan teknologi betonnya, maupun dari segi kepraktisan pelaksanaan pekerjaan dengan desain yang sudah proven paling tidak 10 tahun. Tapi walaupun demikian tentunya masih akan banyak pertanyaan dari Bapak Ibu sekalian. Silakan kalau masih ada yang ingin bertanya. Di sini ada Bu Anissa Mayangsari dan ada Pak Aris Rinaldi yang sedang menseleksi pertanyaan Bapak Ibu sekalian. Nanti saya persilakan untuk disampaikan kalau sudah terrekord. Saya mau tanya dulu sedikit ke Profesor Feng Jin. Sebelumnya mungkin saya mau cek dulu ke Pak Direktur Bina Teknik, Pak. Apa Pak Eko sudah joining kita, Pak? Karena banyak hal-hal. Pak Eko sudah ada, Pak. Jadi mungkin...
Terima kasih. Kebetulan tadi ada pertemuan, jadi mohon izin agak terlambat. Terima kasih. Insya Allah saya bisa.
Mudah-mudahan Pak Eko masih sempat mendengar beberapa presentasi beliau yang kami pernah diskusi waktu Sarasehan di Solo. Tentunya ini perlu ditindaklanjuti melalui waktu itu Pus Air, masih Pak Eko, dan sekarang Direktur Bina Teknik juga. Apalagi tadi Profesor Feng Jin sudah menjanjikan kalau misalnya kita perlu codes atau pedoman atau guidelines yang versi Cina tapi bahasa Inggris itu bisa diperoleh, dan tentunya kita perlu bikin model di Indonesia kalau memang ini aplikasinya cocok dengan beberapa lokasi yang rocknya tersedia dan banyak kebutuhan yang seperti tadi kecepatannya bisa sekitar 4-6 bulan sudah jadi bendungan yang 40-50 meter gitu, Pak.
Siap, insya Allah nanti kami kami tidak lanjuti dalam rangka untuk pengembangan standarisasi atau pembuatan pedoman dalam kerangka pembuatan bendungan, katakanlah salah satu tipe bendungan ini. Demikian mungkin Pak ya.
Terima kasih Pak. Nanti mungkin kami berikan kesempatan lagi Pak Eko untuk menjadi pembahas discussion karena masih ada beberapa hal yang Pak Eko sudah siapkan tapi belum di-sharing, Pak.
Mudah-mudahan.
Saya mau sampaikan dulu kepada Feng Jin sambil Bu Anissa masih menyiapkan pertanyaan. Profesor Feng Jin, before we start with the question coming from my colleagues. I have two questions, and could you please go back to your slides showing the cross-section of the sample of the concrete dams, including the rock-fill concrete dams, whereby you put the impermeable layer on the upstream portion and the gallery.
Okay.
That will be one of the good examples that we have in another concrete dam in Indonesia. Especially, I would like to ask you on how to secure the impermeability of the upstream phase against water in the reservoir.
Yes,
Actually, yes. Can you show the slides first? I'm not so sure.
wait a minute.
The cross-section of the concrete dam with the upstream impermeable and also the gallery just before the construction joins. I think maybe around
this one.
Yes, exactly right. Exactly right.
Yes.
All right. So my question is, in our case for concrete dams, we always have to pay attention how permeable the upstream phase.
Yes.
And in some cases, we can have the possibility of using different kind of material for the impermeable layer. For example, the grout enriched or the grout enriched vibrating or conventional vibrating concrete or geomembrane. And what is your guarantee that using the self-compacting concrete or even high-performance self-compacting concrete, the permeability will not create any problems for impermeability issue on the upstream phase? That's the first question. The second question, still on the gallery, you know also that this gallery sometimes is useful for either inspection gallery or grouting gallery. In one of our concrete dam, there is a kind of concern. Inside this gallery, we experience having water entering the gallery, not from the upstream phase, but we found out that most likely the water is entering through the abutments. And this water entering the concrete materials, creating the so-called lime leaching. And if you notice, if there is a lime leaching, the water will mix with this concrete mortar, and it is turned up to be like a stick of carbon, CO3, I mean. So we have to measure either this incident is progressive or stop. And I do not know how this could happen also in the rock-fill concrete dams, as you explained. So two questions, those related to the impermeability, either the concrete phase or even how to protect if water is entering through the abutments. Please, Professor Fenjin.
Okay, Aris, thank you. They're very interesting questions. At first, actually, the impervious zone in the upstream, we also to set for the conservation reason. Actually, the concrete, the rock-filled concrete had a very similar resistance of this for the seepage. It's very similar for the conventional concrete. So for a concrete dam, usually the concrete dam can resist the seepage by itself. Here in China, we have about 5 or 6 gravity dams whose height is about 40 meters. In these 5 or 6 concrete, there is no impervious zone. All the dam is constructed by the rock filled concrete. In this case, no seepage will be found. So actually, the rock filled concrete then can be used only by RFC. But for the conservation, we use the impervious zone. And in this impervious zone, we can use the self-compacting concrete. In the lab, the impervious zone, the concrete in the impervious zone is much higher than much better than the conventional concrete. So this impervious zone is only for conservation reason. Actually, for the concrete, we can use the rocks in the RFC. And for the galleries, in this gallery, usually we not only for the grouting curtain, we also for the inspection, and we also in some dams we use in this along this. We can show you. Actually, we also set a draining hole, so there is some drainage inside the concrete dam to collect the seepage through the impervious zone water to collect into the galleries. And in the gallery, we can collect the amount of the seepage. It's very few. It's very few. So these galleries, not only to grouting the curtain, it also used for the inspection and also to use drainage. It also used to monitoring. Usually in China, the gravity dam will be monitored in the dam body. Usually we should monitor the uplift. We usually set some instruments along the curtains, and the wire will connect into the gallery. So we will set some monitor instrument to monitoring the seepage. We usually to monitor the uplift, and we also to monitoring the cracking of or some displacement along this interface. And we also monitoring the strain in the important part along, for example, in some instrument like this, in this part. And we also monitoring some temperature of the concrete. And other instruments will be installed at the crest of the dam. So in this dam, we usually set an impervious zone just for conservation. Why we set the impervious zone for the conservation? Because there was some worry about the seepage, not along the rock-filled concrete itself. We worry about the lift surface. The lift surface between the two lifts. There are just like in we show you this. We have to use the green cutting. We have used green cutting, but due to the next lift, after you green cutting, you can get a very clean surface of the lift. But when you when you're placing the rocks of the upper lift, maybe some of the mud or some clay or some debris will be into this lift surface. So the slippage through the surface of the lift is worried about. So we will to prevent the slippage along the seepage, we use the impervious zone. And from the 5 or 6 gravity dams whose height is about 40 meters, we can say if the dam whose height is below 50 meters, we think the impervious zone can be omitted. But till now, due to this is a new technology, it's only about 120 dams. So we are still collect the experience. So till now, we suggest most of the dams will use the impervious zone. But for the future, maybe due to the more and more experienced, and we have to better quality control for the surface of the lift, then the impervious zone can be omitted.
Okay. All right, thank you. I think later on we will discuss also the result of your monitoring on how to measure the seepage from various dams. Now I would like to invite Bu Anissa. Maybe you can directly raise the question by yourself after getting the questions from the floor. Maybe Professor Jin may have some notes to write down the question, maybe one by one, not to confuse with so many questions, Bu Anissa.
Okay. Thank you, Pak Arisman. So, can we start now for the question?
Yes, please.
Okay.
Yes.
So the first question is, what is the main difference between the self-compacting and normal concrete? Is it the slump?
The difference between the self-compacting concrete to the conventional concrete, is that right?
Yes.
Yes, yes.
Yes. Usually, the self-compacting concrete, there have some difference lies on the 2 aspects. One is for the performance. Usually, we can show like this. Wait a minute.
Yeah, you have a slide talking about...
We can show you some like this. We can say if for self-compacting concrete, this is a slump test. So from the performance, from the behavior, you can see the slump is much larger than the conventional concrete. Usually the slump for the conventional concrete is only 80 meters or 120, like that. And the slump is 260 to 280. So it's much, sorry, this is not it's slump flow. And what is this? What is a slump flow? Slump flow because the slump is much higher. So we use another index, that is the slump flow. What is slump flow? The slump flow is the diameter of this how to say, we can measure the diameter from this to this and this to this. So the diameter of this slump will be 640 to 450 and 50. So from the performance, the self-compacting concrete will have a much flowable. And actually, we have to use another the funnel flow. You can see we can test the times of all the concrete will flow empty. This test will indicate if the self-compacting concrete is too how to say if the concrete is too viscous or is too less viscous, then the funnel flow will not locate in this range. So this range, they indicate the viscous of the self-compacting concrete is good, and this good viscous will ensure the self-compacting resistance, performance. This is from the behavior of the concrete. And another aspect is how we can obtain that good workability. This is due to two reasons. One reason, we must use a very, very good superpolitizer. We must use a very good superpolitizer. And the second, in this concrete, the aggregate, the volume of the coarse aggregate is smaller. So we use much, we use more sand, and we use more mineral admixture, and we use some more powders. So the dosage of the self-compacting concrete is different from the conventional concrete.
Okay, thank you, Professor Jin. Please continue, Bu Anissa.
Okay, second question. Itu perlu dijawab siapa yang bertanya nggak?
Boleh, kasih tahu aja.
This is also from Ms. Pak Hendra Jitno. Based on your experience, is there any concerns about cracking due to concrete hydration?
Professor Jin?
Sorry.
Yes.
I can't hear the question.
Okay. Based on your experience, is there any concerns about cracking due to concrete hydration?
Yeah. Till now, we built more than 100 RFC dams. There are no thermal cracking.
No
thermal cracking. Yes, because there are very fewer cement, so very lower temperature rising. Usually, without any temperature control elements, the thermal rise of the RFC in the dam is only 5 to 8 or to 10 degrees Celsius. So the thermal rise is much lower than the conventional concrete or roller compacting concrete. So without temperature control, no cracking, no thermal cracking.
And the next question is, how do you deal with potential honeycombing in the dam due to imperfect concrete compaction?
How
do you deal with potential honeycombing?
Honeycomb.
Honeycomb. It's like,
yes, the segregation of these concrete materials creating honeycomb.
yes, because of concrete compaction.
What's
Concrete compaction? Like maybe because the concrete compaction it's not so good enough, so it will
the deterioration due to the time, the age?
Maybe because of the pumping and so forth. So these concrete elements may have segregation and create honeycomb.
Yeah, I see. Due to the pumping, there are some. This is very important to prevent segregation. That's very good questions. Because actually, in the lab, we can very easily to build a high-performance self-compacting concrete. Yes, during the construction, because of the variation of the raw materials and due to the fluctuation of the moisture content in the sand, the performance of the concrete must be controlled very strictly. And we developed a system to deal with the segregation resistance. We have to use very good performance, very good superposition, and we use a very powerful quality control system. This is, we have a very detailed criteria and procedures. Till now, every dams in China will be supervised by the technical personnel, which is qualified by us. And then they can connect enough experience. Yes, if Indonesia want to build the first dams, we are very glad to train some Indonesia engineers to familiar with how to quality control of the self-compacting concrete. The performance control of the self-compacting, the SCC will ensure no segregation during the pumping and the placement. Yes, this is a very good question. And the experience I cannot explain just in the slide. It's some training. There is some training. Then you can get some experience how to deal with the different situation and to understand how to solve, how to obtain a good performance and to make the stability. And just as we show the stability of the self-compacting, this is very important to keep the self-compacting performance of the concrete must have a long time period. This is very important. So the technique, the segregation and other pumping, blocking will be solved during the construction period.
Okay.
Okay.
Vanessa, continue.
Okay, thank you. The next question is from 3 people who asked the same question. Indonesia is a very highly active seismic country. So how do you deal with potential conflict due to seismic shaking without any reinforcement in RFC mine dam?
Yes, actually, China is also a high seismic intensity regions. Till now, we built only fewer dams in a very high seismic issue. Usually, the dams are built in only, for example, the PGA is about only 2.2 G, 0.2 G, just 0.2 G. And if the PGA of the design, the seismic will reach the, for example, in China, we actually have some region whose design PGA will reach the 0.4, even the 0.5 G, then there are very few experience. But I think because in China, we built many gravity dams and arch dams in a very higher seismic area by the conventional concrete. During our testing, we found that the dynamic experience, the behavior is similar to the conventional concrete. Of course, the tested data is very few, only very few data on the dynamic test because it's too expensive. And if we have to build in a very high seismic area, such as, for example, the PGA is reached to 0.5 G or 0.4 G, I think there will be some special testing on the performance of the dynamic property of the RFC, I think.
Okay, good.
Okay, thank you. And the other question is about the construction cost. Is there any rule of thumb to guess the cost of RFC dam? Maybe how many dollars we should investment to per meter cubic of reservoir storage? Or and the other question is, what is the difference of CapEx cost for embankment and Antashi Dam? Maybe everyone wants to know about the cost of the
RFCD.
RFCD dam,
Yeah.
compared with the embankment dam.
Oh,
Do you have clear understanding about the question? The first
this is ask the difference between the rock embankment dam and rock fill concrete dam. You right?
Yes, there are two questions. The first question is, based on your experience, maybe you have a data about the cost of rock fill concrete dam in comparison with the volume of the reservoir. Maybe a certain million US dollar per cubic meter of reservoir volume, or another question is related to the comparison of cost of construction for rockfill concrete dam against rockfill embankment dams.
Yeah. I see. Actually, in China, the concrete of the RFC, the unit cost is about the whole cost is about 300 RMB. That is about how much? It is about only $50 US. 50 US dollars per cubic meter rock fill concrete. But I don't know, because there are different countries. There is the cost of the cement, the cost of the labor, the machinery, and other materials. But in China, in this case, we can say for conventional concrete, it's usually is about 360 or 380. That means about, I think, is about 60 or 70 US dollars. 60. So compare to the conventional concrete, the cost of the RFC is only 80% of the cost of the conventional concrete, usually like that. So this is about cost. Of course, usually in China, the rock fill dam is cheapest, because the cost of the construction dam material is cheaper. But usually for a rock fill dam, you have to build a spillway. So if you consideration the spillway and the dam, maybe the concrete dam may be cheaper, or the rock fill dam may be cheaper. So it must be through the technical and economical comparison. So in China, if the foundation is very poor, then we usually to build the rock fill dam. But if the foundation rock is very good, we have a good solid rock foundation, we build a concrete dam. And then when you build a concrete dam, the RFC dam is a significant economic than a conventional concrete dam.
Okay, I think, Professor Jin, we have a lot of remaining questions, but unfortunately, the time is already overdue.
Yes.
And we know that we will send you, if you do not mind, by email all the remaining questions, and hopefully you are still kind enough and generous enough to answer those questions later on.
Okay. I'm very glad to introduce this technique and answer the questions from Indonesia colleagues. I'm
Okay.
very glad to be connected with you.
Of course,
I'm
from
very honored.
yes,
I'm very honored to have a chance to discuss with the Indonesia colleagues. Thank you, Alice.
okay. So we know that in Beijing now it is almost 6 p.m. So maybe it is time for you to take a rest and continue with your time. And we would like
Thank
to
you.
take a photo together, and that will be one of our documents in INACO events, that we have a very special guest expert explaining about the Rockville Concrete Dam. Let's take a photo together.
Okay.
Please, everybody, open the camera, smile, and cheers.
Cheers.
Okay.
Cheers.
Thank you so
Okay,
much,
thank you.
Professor Feng Jin. Take a
Thank you.
rest, and we will see you again next time. Good luck.
Good afternoon. Good.
Okay.
Goodbye. Goodbye. Bye. See you.
Siap.
Thank you. Thank you. Thank you.
Oke, kalau begitu kita
Okay,
bisa
bye.
bye-bye. Terima kasih buat Bapak Ibu sekalian yang sudah menyampaikan pertanyaan. Nanti Bu Anissa akan menyampaikan secara tertulis kepada Profesor Jin yang mudah-mudahan masih akan dijawab. Dan sekarang saya serahkan floor kepada Pak Joko untuk melanjutkan dengan kita jeda.
Terima kasih.
Lucky draw dulu, Pak.
Oke, terima kasih Pak Firman. Bapak Ibu sekalian, kita redakan saraf-saraf kita dengan lucky draw. Silahkan Mas Irfan, tolong perwakilan dari Pak Tri. Nanti tolong Pak Tri bisa sampaikan kata stop. Nah, ini kita yang kuning dulu, Silakan pegang Pak Tri. Mas Irfan, siap-siap untuk menyampaikan kata stop. Nanti Bapak Ibu sekalian akan terdaftar di sini. Mulai dari Pak Abdul Godi Maji sampai dengan di sini terdaftar ada 530 sampai Pak Suhartoyo. Silakan Pak Tri Bayu Haji.
Ini
Berputar.
Terus dilacak dia muter. Jadi kapan Pak Tri bilang stop, dia dapat lakinya, Pak.
stop.
Wah,
246. Sebentar, ini namanya banyak sekali, jadi harus kita cek satu-satu. 246. Nah,
2 ditambah 4, 6.
iya. Angka cantik.
angka cantik.
Pak Soko sing nyekel. Jangan Pak Dewi.